Hello and welcome to our robot design review. I'm Tim and I am part of Lego to the Lake, one of the competitors in the 2020 SCFLL COVID Challenge, Alumni and Mentors competition. In this video, I'm going to walk you through our robot, our attachments, our jig, and some of the decisions that we made, why we made them, and how they helped us perform better in the competition. In the description, you can find links to our runs separately and the whole competition if you're interested in watching what the other competitors had to offer. To start, this is our robot. These are our 4 attachments, and this is our jig. Our primary goal in all of our designs was to minimize our time spent in base. As mentors, we knew that many teams spend most of their time at the board with the robot in base, not scoring any points. We knew we wanted to maximize our time out of base so that we could maximize points scored. Let's get started. We'll start with the first attachment to go on our robot. We line this run up and set up the robot prior to the start of the match. We chose this run to go first because we knew it had the longest setup time. It required the most careful setup in base, and it required plugging in a wire for this sensor. Ideally, we wouldn't have put a sensor on the attachment at all, but we needed a sensor to follow this line going this direction. And on board the robot, we did not have a place to put the sensor such that it would not be in the way of other missions. So we were forced to put it on the attachment. Pushing the robot into a corner to start, whether it's the corner of the board or a corner we created with the jig, allows us to quickly and easily line up the robot without having to look to make sure we have it perfectly aligned with a line that's marked on the board or a letter or anything like that. This saves us a lot of time in base. As far as how this attachment works, we'll start from the front and work our way to the back. This is one of our most complex attachments, as far as having the highest number of moving parts. We only have 2 auxiliary motors, both of them located on this end of the robot. This box on the front to collect the germs is actuated by pushing the box up against the sink and dumping the germs out into the sink. This is what we call passive actuation, where we do not need a motor to make this move. This is immensely helpful for 2 reasons. 1, it leaves our motors free to do other functions, which I'll explain in a minute. And 2, it greatly simplifies the mechanism because all that this box needed was a pivot point. It did not need any arms, gears, axles, or other means of transmitting motion to enable it to flip like this. You may be wondering, if we push this box up against the sink, what happens to this bar that's sticking out at a bizarre angle? And why is it there in the first place? To answer the first question, this bar is simply spring-loaded, so it pushes back. The second question, as this robot follows the line down the board, it encounters a water. We wanted to be able to collect all the waters and bring them back to base, but we knew that if we pushed that water with us, down to the germs and then handled the germs and that water at the same time, we would be forced to put that water in quarantine as it would be contaminated. We didn't want that to happen, so we came up with this bar to push the water out of the way and off to the side of the robot. This is also a passive attachment. It is passive in its interaction with the water in that it does not push the water via a motor, and it is passive in its interaction with the sink in that it gets pushed out of the way simply by the robot moving forward. Moving to the other end of the robot for this attachment, we have two arms. This one, the Gerhard arm, actuated by a 4-bar linkage, and this one, the bat arm, simply rotates. The Gerhard arm also has an interesting gear train, a large gear driving a small gear, driving a worm gear, driving another spur gear. This setup allows us to have relatively controlled motion of the arm and move it at the speed that we wanted. While the robot is out running its run with this attachment, the jig is removed from base so that when the robot comes back into base, it has room to come all the way into base easily. This is also critical to pay attention to as you build attachments, that they're not so large that they're difficult to get back into base at the end of a run. This sensor is then unplugged and the whole attachment lifts off. See how quick that was? That is part of our strategy to minimize the amount of time in base, and that was critical to our ability to run as many missions as we did. Next up, we have the hospital attachment. From here on out, I will be demonstrating how the attachment goes on, as well as how it goes off. I'll do this because they're so fast they fit in the video, and that is a critical part of why we were able to run these missions so efficiently. This is our hospital attachment. In case you hadn't noticed, I can't stress this enough. Minimize your time in base so that you can maximize your time out on the field. For some teams, that may look like having no or only one attachment, and that's great. For other teams, that may look like something like what we've done, where all the attachments are very quick to drop on and pull off. In a similar fashion, your setups in base should also be very fast. This one, you ready for this? It's set up. This attachment also has another rare feature called soft points, or soft fingers, or just soft bits, whatever. Soft bits are things that are intentionally a little bit flexible, a little squishy. These black tubes are very popular in Lego worlds for being able to be soft actuators, soft attachments. What this allows is this allows for more error with the same result. For example, as part of this arm's mission, it goes down, the syringe is released, and sometimes the syringe ends up under the arm like this. The arm then returns back to the upright position. If these were static fingers or stiff fingers, they would not allow the syringe to stay here while the arm returned to its upright position. Either the arm would get stuck or the syringe would get knocked over or broken. Either way is not a good end for us, the team. But with these soft components, we now still control the syringe and can control it all the way back to base. Soft components are also helpful if you think you may run into a mission model. Remember that arm on this attachment? Notice how the end of it is flexible. It's another soft component. That's because we were having issues on the germ hopper down there with this getting stuck. So we made it soft and flexible so that it would just flex around the legs of the germ hopper and we would not get stuck. Other features of this arm include a string that actuates the top of the arm so that we stay under the 12 inches. But we needed the arm to be able to reach out forward when we lower the arm. So the string allows this. Now you could have used more of these instead of the string, or you could have used some axles instead of the string or something like that, but the string provided a light and compact solution to this problem. Another thing I want to point out on this arm is the use of ball joints here and here, and a tie rod here. What a ball joint does is allows rotational motion this way, and this way, and this way. Your shoulder is a ball joint. Similarly, we can use ball joints on the robot to turn rotational motion this way into rotational motion this way. Other places that you might see ball joints that you could get some inspiration from would be your car's suspension and steering. This attachment also uses some fun rubber bands, such as the one used to keep the pacemaker gripper closed, and the 3 used to return the arm back to its upright position. Further, this arm is held onto the robot via these 2 clips. These clips are actuated together on the same axle and held down with rubber bands. We admit, again, this is not ideal. Ideally, this arm would sit on the robot with no need for these clips and make adding and removing this arm from the robot even faster. But due to constraints in our design size, notably that we didn't have any further support structure out front, we couldn't do this. And without these, as the arm moves forward, it has a tendency to lean forward and may lean so far that it pops up off the motor mount, causing it to return back to vertical prematurely. Despite these clips though, you'll notice this still pulls right off and drops on almost as quickly as it would without the clips. As the robot comes back into base after this mission, hopefully with the syringe, this attachment is removed and the next attachment is added. You'll notice at this point in the videos of the runs, if you watch those, that my dad picks up the robot and turns it to here, while I am waiting with the jig and next attachment in hand. We discovered that this process was the quickest process to setting up our next run. We discovered this through practice. Here I want to highlight the importance of practice and teamwork before and during your event. Our next attachment, our chemistry run attachment, our smallest attachment, also uses the clips and goes on like so. The robot then goes against the jig and against the wall. Again, easy and fast. You'll notice in our run videos, we don't spend much time in base. This was our goal because we knew that we were capable of completing all the missions on the board. This attachment runs down along the chemistry mission and flips each chemistry block depending on whether or not it should be flipped. After passing the chemistry, it should have all the black bricks facing north and all the white bricks facing south. We use a light sensor pointed sideways for this mission to detect whether it sees a black surface or a white surface and trigger the arm accordingly. An interesting part of this arm is that it is a linear slider. We rotate and the arm slides. This is also a linear slider, releasing a pin and letting the arm drop. We chose to do this arm drop instead of a powered arm for a couple of reasons. One, mechanically simpler, and two, because we wanted this arm to lay perfectly on the table, not try to lift the front of the robot, and also not accidentally stop too high up. Again, when the robot gets back to base, the jig is removed before the robot gets back to base. This attachment is pulled off. My dad again turns the robot for me while I am waiting with this attachment, our fourth and final attachment, to go on the robot. Again, this run starts against the wall and against the wall. This behemoth attachment uses this U shape to collect the waters it passes as it goes out, carries many items on this shelf to the house. This attachment has some great examples of linkages on the dumper and on the door arm, and even here on the syringe release. This attachment also, like many of the others, uses passive parts to complete missions. This black piece sticking out in front of the attachment is used to raise the flag on the screen in the house. Finally, this attachment extends the touch sensor bumper beyond just the bumper that is now hidden back in the U shape. This arm that is extended to the side, that moves back and forth, presses the touch sensor, along with this button over here, when pushed backwards, presses the touch sensor. Let's discuss a little bit about the three sensors we used on this robot. We have one light sensor pointed sideways. This is used in the chemistry mission, and as the robot proceeds past each block in the chemistry mission, it detects whether the block is white or black facing north. We use the touch sensor in all four of our missions. Notice that as I push this front bumper, the back bumper also moves. And there is only one touch sensor located here underneath the robot. These two front and rear touch bumpers are connected via a rod that runs through the middle of the robot. We chose to do this to limit the number of sensors we needed on board the robot. Our third sensor is on an attachment. As I said in discussion of this attachment, we acknowledge that this is not ideal, but we chose to run this attachment first so that we could minimize the amount of time spent fussing with this wire. By running this attachment first, we do not have to plug this wire in under the pressure of time, and thus we can carefully plug it in, make sure it's secure, and make sure the sensor is functioning before we start the run. At the end of the run, all we have to do is squeeze and pull. Some final aspects of our robot design that I want to discuss a little bit about are robustness and neatness. Notice that on this robot, you can barely see the wires. You see them poking out here, just a little, and you see 2 sensor wires poking out here. We hid most of our wires under the brain and under this panel. This provides some great wire management so that as we go to put on attachments, we do not have to hold wires out of the way or pull them back or anything like that, thus further reducing our time spent in base. Finally, notice the rim around the edge of the robot to support the outside of the wheels, with a well-supported motor on the inside to support the inside of the wheels. This makes sure that our wheels do not gain camber, which is this. This is negative camber. This is positive camber. By adding structure to the outside and ensuring our motors were securely fastened on the inside, we kept our wheels very stable, ensuring repeatable motions out on the board. Finally, I want to demonstrate our robot's center of gravity, specifically front to back, as it is roughly symmetrical side to side, and thus the center of gravity is roughly in the center, side to side. Ideally, your center of gravity is perfectly over your drive wheels. Ours is not perfectly centered over the drive wheels, but it's very close. You can see that as I pick the robot up with pins that allow the robot to rotate, from this point, only 2 pegs forward of the center of the drive wheels, the robot is roughly balanced. We did this by shifting the brain backwards behind the drive wheels and placing the motors in front of the drive wheels. This balance greatly increases our reliability in turns because our drive wheels are carrying most of the weight of the robot and thus have more grip. So that's an explanation of our robot. I hope you've learned some things from this video and you'll take them back to your team to improve your team's robot designs in the future. As I mentioned at the start of the video, if you're curious to see our runs, both during the competition and the best run we've filmed ever, check out the links in the description. Good luck, remember to have fun. We look forward to seeing all of your amazing creations.